Hello, this is about Möbius transformations again, and it's about what you have to write to explain why this method works. There'll be another video clip which will explain the theorems which I'm going to mention now. So I'm going to take the same example, w equals z plus 1 over z minus 1. And you'll have a particular z locus to investigate with that transformation. Suppose the pole is inside the z circle. For example, the z circle is mod z equals 2, and the pole, which is z equals 1, is inside it. Then you can say the intersecting chords theorem implies that 1 over z minus 1 star is a circle, follows a circle. Right, notice I've just got the bottom bit of the transformation. I'm not bothered about the z plus 1 at the moment. I'm just bothered about the 1 over bit of it. And I've got a star there, a conjugate. And I'll explain why in the next video clip. Okay, but you can see if that's so, to get from that to that is not hard. Firstly, we've got to take the conjugate again to get 1 over z minus 1. But once we've got 1 over z minus 1, that is just equal to that. So to get that from 1 over z minus 1, you've just got to double it, scale it up to twice the size, and add 1 to it. So to get from here to here, we've got to take the conjugate, scale up by a factor of 2, and add 1. But taking the conjugate, conjugation, scaling, doubling it, translation, moving it across, and for that matter, rotation, which we don't have here, but we would have if, for example, our transformation was that, then we would have a rotation. All those, conjugation, translation, scaling, rotation, all map circles to circles. If you flip a circle in the x-axis, in the real axis, it's still a circle. If you shift it across, it's still a circle. If you scale it, enlarge it, or reduce it, it's still a circle. And if you rotate it, it's still a circle. So we can write conjugation, translation, scaling, rotation, map circles to circles. Therefore, it follows not only that that's a circle, but the whole W locus is a circle. Final thing you have to cite is why you can get a W diameter from a Z diameter. And you say symmetry implies that the Z diameter in line with the pole maps to a W diameter. That symbol means maps to Z diameter in line with the pole maps to the W diameter. Okay, that's the case when the pole is inside the circle. If it's outside the circle, it's only a slight difference. So if it's outside the circle, so suppose the Z locus was mod Z equals a half, a circle of radius a half, and 1 is outside it, then it's all the same except the theorem is called the intersecting sequence theorem. The rest of the explanation is exactly the same. The third case is if the pole is on the Z circle. Now, in that case, the theorem doesn't have a special name. It's just called a circle inversion theorem. So you write a circle inversion theorem implies that that is a line all these transformations, conjugation, translation, scaling, rotation, map lines to lines. So the W locus is a line. Then you don't need to have any equivalent of that, because if you remember, if the W locus is a line, really what you do is you find two W points on it. You find two values of Z, convenient values of Z, find the values of W, and those two values of W will be enough to tell you it's what line it is, unless one of them is the pole itself, in which case you get W equals infinity, which just tells you that it's a line. But any other 2 points on the W line tell you what line it is.